Hello, class, and hopefully you're not getting too bored of the videos here. We're going to look at something that's really fun in chemistry. We're going to look at titrations. And some of you may have done titrations before, maybe not. We're going to look at a specific type of titration, an acid-base titration. And just a quick review, if you have forgotten what we've been talking about with acids and bases. Remember that a strong acid combined with a strong base always forms water. We have the hydrogen ions and the hydroxide ions, they form water. A neutralization reaction, just recall, are equal amounts of the hydrogen ions and the hydroxide ions reacting together. It makes a neutral solution, and neutral solution is a pH of 7. That's a very thick line. We'll make that a little thinner. And then this is just a picture of an acid-base titration, or any titration really, a setup of what that would look like. Oftentimes, if chemists aren't sure and they would like to analyze the content of a particular solution, we're just going to talk in this case about acids and bases, they don't know what its molarity is, something like that's an unknown. They can perform this titration in order to find the necessary information in order to calculate that. Let's go on and look at how that's done. When we mix a measured volume, so we're going to know our volume and we're going to know our concentration of a titrant. So we'll call this the titrant in the burette. This right here is the burette, and titrant is poured into the burette at some volume. This little stopcock is what, when we turn it, it allows the titrant to fall through into the analyte. The analyte is what we're going to analyze. It's the solution that we're not sure about, something about it. Maybe we don't know the concentration of it. So we'd like to analyze this. We can know, as we do this titration, we put color indicator in here, and we can know at what point we have a neutralized solution. If we choose an indicator whose color will change at a pH of 7, when we put equal number of moles of our titrant mixed with equal moles of the analyte, we know that that is the equivalence point. We'll talk a little bit more about that in just a minute. And we know that at that point, the number of moles of the titrant is equal to the moles of the analyte. So we can then calculate the molarity. So things that we need in order to set a titration up, obviously a ring stand of some sort with a clamp attached to it that is a burette holder or a test tube holder, and it can hold this glass burette. We need the standard solution. The titrant is going to be a solution with a known concentration, so we'll probably have to make that. We'll need the burette, we have that right here, the ring stand, and an Erlenmeyer flask. Usually the analyte is placed in an Erlenmeyer flask. That helps to avoid splashing of the titrant. So when we perform a titration, an acid-base titration, the titrant is added very, very slowly to the analyte until exactly enough has been added to react with all of the analyte. We call that the equivalence point, when the amount of titrant reacts exactly with the complete amount of the analyte, not more, not less. And if we choose an indicator such as, here's just an example, phenolphthalein. It is clear when it's basic. It just turns pink when it passes pH 7. So this has gone too far. If you see this person, they did a nice slow job. They're swirling their flask around, mixing it up. And sometimes as you drop your base in, it will turn a little bit pink in that one spot where there's a higher concentration until you swirl it around and it mixes in and it goes clear again. The point at which you make a drop into your acid and it turns just a little bit pink and stays pink when you swirl, just slightly pink, that right there is the end point. If, though, you accidentally knocked your stopcock or put a few too many drops and went too far, it will be darker pink. That's too far. You've overshot your endpoint. And literally, it's just within a drop that you should be able to perform this lab technique. Here, we have our neutralized solution. The indicator has changed color. It's important to realize that your burette is going to be volumetric. It has measured amounts on it. So when you begin your titration, you read the burette first. You make sure you know how much titrant is in there. And then once you reach your endpoint, you read the burette again, so you know how much is in there. You could take that difference to find out how much of the titrant that you used. So now let's look at a graph, because graphs are just really nice in science. We can see what's going on visually. If we graph pH versus the volume of our base that we add, let's say we're titrating an acid. You can titrate either direction. I'm going to generally refer to the sodium hydroxide as the titrant, and because you're going to be doing an experiment like that. So in our case, this time we're going to add sodium hydroxide as the titrant, the base, and our acid is unknown. When we do that, we start out adding sodium hydroxide. When we add, in this example, they're saying the amount added in milliliters. Oh, we had 5 milliliters, 10 milliliters, 15 milliliters. You know, it's 20 milliliters. It's really, the pH is really changing very, very little. And the next section, we're going to talk about why that is. But for now, realize that there's very, very little change that goes on for this first part. Once we get really close to the equivalence point, tiny volume of that base dramatically affects the pH. And we call that point right here, that's the equivalence point. The point at which we get a rapid increase in pH. We reach this equivalence point. The moles of the titrant is equal to the moles of the analyte. They're reacting exactly at that point. We get a color change because we've chosen our indicator well, and it's indicating a color change at pH 7. And then if we overshoot the endpoint and add more NaOH, we can continue to add NaOH, and we will see very little change again in pH once we overshoot the equivalence point. And hopefully you won't do that in your experiment. But this is the equivalence point. It's the point that we get our great spike in pH, and the moles of the titrant is equal to the moles of the analyte. Let's look at an example here. I'm going to have a problem. I would like to know how much volume of a base I'm going to need to add to an analyte. If my base has these qualities, let's say I have a 0.1 molar sodium hydroxide solution, and I am going to titrate 50 mils of a 0.200 molar nitric acid solution. So there's my problem. First, I'm going to write this whole problem out. I'll kind of color code this for us a little bit. There's our base. Here's our acid. We can also, this is a strong base and a strong acid, we can simply write the equation like this as well. We only have one hydrogen and one hydroxide ion being contributed. It's a 1-to-1 ratio. We're forming one water molecule. If you would like some advanced proficiency, here's an idea for you. Pick an acid and or a base that this is not true. When it dissociates, it has several hydrogen ions. In that case, when you do these calculations, not only will you do the calculations we're doing here, but you'll have to add in the mole-to-mole ratios into your calculations. So if you'd like some advanced proficiency, you can set up a problem like that for yourself. Just make one up, kind of in this format. Just use a little bit more complex acids or bases. Now, let's go back to this very simple one. Just for regular class, for everybody else, for proficiency, I want you to know how to do this with acids and bases that are that just give 1 mole of hydrogen ions or 1 mole of hydroxide ions. So you will not have to worry about doing a mole-to-mole conversion in these. Nitric acid, we can also write, again, like I said, we can write this out as the hydrogen ion and the hydroxide ion form water. What do we know about that acid, about that nitric acid? We have a lot of information here. We know from up here that it is 0.2 molar or 0.200 moles per liter. We also know from up here that we have 50 milliliters of it. I'm just rewriting that as 0.050 liters because we never put milliliters in formulas. We use liters. So we know that. What do we know about the base? Okay, we know that it is 0.100 molar. So I wrote that right down right there. 0.100 moles per liter. And do we know the volume? No. That's what we're looking for. Find the volume of it. So remember, in a neutralization reaction, the number of moles of the acid is going to equal the number of moles of the base when it's neutralized, when the pH is 7. So that's what we're wanting when we titrate. We're going to look for that pH of 7. We're going to look for the point at which the moles of the acid is equal to the moles of the base. So when those are equal, the moles of the acid, do you remember this little formula here? The concentration is going to be in molar or in moles per liter. And when we take the concentration and we multiply it by the volume in liters, the liters cancel out, and I simply am left with the number of moles of that substance, right? So we could even write this as at the equivalence point. When our titration is at the equivalence point, the concentration for the acid times the volume for the acid is going to be equal to the concentration of the base times the volume of the base. Because at the equivalence point, the moles of one equals the moles of the other. And we know concentration times volume gives us moles. So this is really, once you can set this up like this, it's really not difficult. Let's just plug values in for these. My concentration of the acid then is 0.200 molar, or moles per liter. So when I multiply that by the liters cancel out and I'm left with moles. That's going to be equal to the concentration of the base is 0.100 molar or moles per liter times some volume. I don't know that volume right now. This now is a simple algebra problem. Here's our variable, and we have terms here that are being multiplied out. If I divide this side by 0.1 molar, I have to divide this side by 0.1 molar. And when I do that, I end up, these cancel, and I get V equal to 0.200 molar times 0.050 liters, all of that divided by 0.1 molar. That ends up giving me 0.100 liters. And if I rewrite that, I can say the volume is simply equal to 100 milliliters. So when I answer this, it takes 100 milliliters of 0.1 molar NaOH to neutralize 50 milliliters of 0.200 molar nitric acid. Oh, one thing I almost forgot, my sig figs. I need to be able to have 3 sig figs, so I need to put a decimal point right there to indicate that I have 3 sig figs. And that's our answer. So I'd like you to stop the video right now, please. Try this problem on your own. Write it down. See if you can do this on your own. Start the video back up, or if you'd like, go ahead and go through the whole video, but write the problem down, and the answer is on the next frame. Make sure you can get it correct. There's an additional example as well. This will be to make sure that you're proficient at this type of calculation. Here's your answer. Hopefully y'all got that. If you didn't get that, or if you feel a little uncomfortable and you'd like to try another problem, here is another practice problem, and the answer is on the next frame. Okay, here's the answer to that problem. And we're going to do another type of problem now. We're going to use an example that you'll want to pay particularly close attention to because you're going to be asked to set up an experiment that's a lot like this. So let's say we want to set up an experiment and we have some hydrochloric acid and we don't know what the molarity of that hydrochloric acid is. We'd like to find that. We're going to set up a titration in order to find what the concentration of that hydrochloric acid is. And we're just going to pick 37.50 milliliters of hydrochloric acid. That's what we're going to start with. We're going to titrate that with a base. We're going to use potassium hydroxide, and we're going to make our own molarity. We're going to make our own solution, our stock solution, with a known molarity. It's going to be 0.1500 molar, or moles per liter, of potassium hydroxide. And we're setting that up in the lab, and we do the titration. We don't overshoot the endpoint. We get the equivalence point just perfectly right on, and we find that we end up using 75.00 milliliters of that base to reach the equivalence point. How can we use this information to determine the concentration of our hydrochloric acid? Well, remember, at the equivalence point, we have the number of moles of the acid is going to equal the number of moles of the base. Okay, at the equivalence point, they're going to be equal. And if you'll remember, the concentration in molarity or moles per liter times the volume in liters, we get the liters canceling out, right? Because concentration is, let me write it down, moles per liter. The volume is going to be in liters. Our liters cancel out. When we multiply those things together, we get just the number of moles. Now remember, the moles of acid at the equivalence point is going to equal the moles of base at the equivalence point, right? So we can set this problem up in a really simple way. Since we know the moles of acid equals the moles of base at the equivalence point, we can say the concentration of the acid times the volume of the acid is going to equal the concentration of the base times the volume of the base. And this turns into a really easy problem. So the concentration of the acid is, we don't know. That's what we're trying to find out, right? What is the concentration of the acid? The volume of the acid we know because we started with it right here. And it's 37.50 milliliters. That's going to be, I'm going to just convert that in my head, 0.03750 liters. That's going to equal our concentration of our base. Remember, we made our stock solution. We know its concentration is 0.1500 molar. And we know the volume of the base because when we looked at our burette before and after the titration and took the difference between them, we found that we used 75.00 milliliters, which is 0.07500 liters, and that doesn't really fit there. So again, this is a very simple algebra problem. I'm going to multiply these two numbers together, divide them by this number, and that should give me the concentration of my acid, of my hydrochloric acid, and that ends up being 0.3000 molar for my HCl. And I would use 4 sig figs because I have 4 sig figs in all of these numbers here. Make sure in the lab you don't limit yourself by not taking into account all the correct sig figs when you measure your all of the volumes and of what you're doing, as well as the mass. You'll be doing some measuring of mass. Now that you know how to do this, you can go in the lab and do something very similar. You get to design your own experiment. So once you've watched this video, you understand how this works. I want you to make sure and watch a couple more videos. They are shorter than this one. They're on the Moodle website. They are the lab technique videos. And I want you, oops, I didn't mean to do that. I want you to watch those because they show you how to set up a titration and how to actually set the everything up and talk a lot about the lab techniques. I apologize, the gal isn't tremendously exciting, but I think it's only about 6 or 7 minutes. There's another video as well that's just a couple of minutes long, and it's showing some students actually doing this titration and reaching their end point just right. They're just swirling their little Erlenmeyer flask around and reaching the end point. Here's a picture of what you're going to get to be doing. Chemistry students having fun doing titrations in the lab. You're going to take household vinegar and you're going to titrate it with a known solution of sodium hydroxide. You're going to have to make your own solution of sodium hydroxide. So you'll have to figure out how to do that. You have to figure out how to set your whole experiment up and write down your procedures telling me just how you're going to do it before you go into the lab and do it. So it should be really fun, and in the end, you'll be able to actually calculate the molarity, the concentration of the acid in household vinegar. So it should be very exciting, and I look forward to seeing you in class. If you want to do the advanced proficiency, again, you can do some more complex titrations of acids or bases that require a little bit more complexity. So see you in class.